Welcome back, AP 10.7 Kinetic Molecular Theory. You can put your calculator down for a little bit because this is a section about explaining. Okay. KMT, Kinetic Molecular Theory, as you see, there are 4 learning targets. So this must be a big topic for them. So first, take a minute, read the learning objectives. What does AP expect you to be able to master? So number 1, I want to point out this distribution curve. You're going to see it in the notes in just a second. You need to make sure you understand that graph and how to use the data to explain it. Okay. This equation is going to come up more, and I'm going to make a note, chapter 14. Okay, so you don't have to worry about it here too much, but you do need to understand how kinetic energy changes speed. Okay, so take a minute. There's a lot of information in here with speed, with temperature, and notice that word again, the distribution, Maxwell-Boltzmann distribution curve. So take a minute, annotate, and then come on back. KMT was developed to explain gas behaviors, gas movement. So why do gases behave a certain way? So this model explains why real gases are very close to ideal gases at particular temperature and pressure. So if you have a certain pressure and temperature, real gases can get very close to be called ideal gases, okay? But you have to have a certain temperature and pressure, and we'll get to that in this video. So what about the gas laws that we've talked about versus KMT? How do we explain? So when you are trying to basically justify to AP while something increases or decreases or remain the same, these are your explanations. This is what you're supposed to be striving for on your own to be able to explain to AP. In Boyle's law, it was about pressure versus volume, okay? As long as temperature and moles were constant. So the volume of the container decreases, particles collide with the sides more often. And remember, you went from a big container to a small container. So what did you do? You brought the particles closer to each other. So you have more collisions. More collisions increase pressure of the container. On the flip side, if volume increases, so you go to a bigger box, the kinetic energy remains the same. And why? Because you didn't change temperature. It has nothing to do with volume. So the gas molecules must travel farther to hit the walls of the container, and that leads to less collisions. Okay? That's how you have to explain like a gas. Charles' law looked at the relationship between volume and temperature while pressure was constant. So when temperature is increased, particles can move faster. And why? Because they gain energy. What energy? Kinetic energy. So causing more and stronger collisions with the side of the container. The volume increases to keep that pressure constant. Okay? So if temperature increases, they're faster, they're stronger, they have more energy to strike the container. Avogadro related volume with moles. Okay? If you add more particles to the container, you have more collisions. And why? Because you took up some of the empty space with particles. Okay? You invaded that empty space by adding more. And by increasing the volume, this is what allows us to keep that pressure constant. So you have more collisions. You don't have more energy, but you do have more collisions. So be very careful when it comes to collisions versus energy. Gay-Lussac looked at pressure versus temperature. If the temperature increases at constant volume, the molecules are faster, aka velocity or speed, whichever one you want to look at. You have more energy. Okay, so with temperature is definitely related to kinetic energy, okay? And temperature also relates to speed. Will they be faster or slower, okay? So the more collisions with the container of the walls, then the change in the momentum in each collision increases. So molecules will actually strike harder. And I'm going to show you a diagram of how do you know in a picture if they're striking harder versus less impact. So more collisions will occur by changing that temperature. With kinetic molecular theory, there's actually 5 items that were discussed why a gas can actually be considered ideal. So in order for a gas to be ideal, it must meet all 5 criteria. And if it doesn't, then it's what we call a real gas. Okay? So number 1, gases are composed of molecules that are in continuous motion. They travel in straight lines, and they will only change directions if they collide with each other or the walls of the container. Okay, so as you see, like these arrows, this molecule is going to collide down. This one hit the wall and then change directions. So pay very close attention to the arrows because they are very, very important. They tell you a lot. So in this case, these arrows are telling me about direction. So did they, are they headed towards the wall and just haven't impacted it yet? Or did they hit the wall and then bounce into a different location? Okay. I like to think of this one like playing pool. When you play pool, you strike the white ball, it hits all the other balls, I said molecules, but they're pool balls down at the end of the pool table. And as soon as you hit it, all of the molecules, aka the pool balls, they all go in different directions. That's literally what gases do. There's no rhyme or reason. They go whatever direction they want. The pressure exerted by a gas in the container results from collisions. So if you change the pressure, you have more collisions between the molecules and the containers. So remember, they're not bonding. They are attracted and repelled, but as soon as they get close to each other, then they collide and then they bounce into a different direction. The magnitude of the size. That word magnitude is very important in chemistry because magnitude means size. Of the pressure is determined by how often and how hard the molecules strike. Now, you need to pay very close attention to the arrows and the size of the arrows. So when you have a molecule that has like a small arrow versus a molecule that has a longer arrow, that doesn't mean distance. That means striking force. An arrow that is longer obviously has a harder striking force with the wall versus a little arrow has a small or low striking force. Okay? This one will have more of an impact when it strikes that container or other gas molecules because of the length of the arrow. So pay very close attention to the arrow. The longer the arrow, the harder, the more force it's striking the container. Kinetic energy, big time, okay? Directly proportional to temperature, okay? Unfortunately, ladies and gentlemen, you can't say this on the AP test, okay? Kinetic energy, if you increase kinetic energy, is because you cranked up the temperature. And when you cranked up the temperature, you got the molecules to move faster. So you just affected speed. You also have more collisions. Okay? But you can't say the words directly related. Even though it is, AP doesn't want to hear about the relationship. They want to hear how they're connected to each other. So kinetic energy increases as temperature increases. And you can get them to go faster, which means velocity and speed. Okay? Let's talk about this word negligible. And I put it, the definition right here. Unimportant as to not worth considering. Gas particles are so negligibly small, negligibly as in not important. It's not worth considering talking about. They're so small compared to the distance between them that the volume of the individual gas molecules, they must be pretty much zero, negligible, okay? So remember, all 5 of these have to be met for a gas to be considered ideal. The problem is the volume actually matters. So when we get to the last video in this chapter, this one's actually untrue when it comes to real gases. Intermolecular forces, you're going to hear me talk about this in chapter 11. Intermolecular forces, it's the forces between molecules. I didn't say bonding. The forces between are also negligible. The problem is, it's not true for real gases. For ideally, great. Real gases, because what happens there's actually attraction and repulsion. I never said bonding. Bonding is something different. But there are some gas molecules that are attractive to other gas molecules where they want to be kind of close, not touching, just close. And there's some that actually repulse each other to where they get actually farther apart from themselves or the containers. So with each other or the container walls, therefore their collisions are what's called ecstatic. Do not involve a loss or gain of energy. Okay, so even though they're attractive or repulsive, you're not losing and gaining energy because of that. So kinetic energy is not changing. So we do have 2 of them that definitely are not true for real gases. But ideally, all 5 of these are met. So be very careful with the word negligible. Okay, negligible means just hardly has any effect. Okay. The Maxwell distribution curve, very, very, very important. You're going to see this curve pop up a couple times. We're going to look at the scenario one of 2 ways. Same gas, and it looks like we're using nitrogen, different temperatures. So what do we know when we change temperature? Well, as the temperature of nitrogen increases, I have more molecules moving at higher speeds. The average speed is increasing. Okay, and there's actually some molecules that are actually slower versus faster. So notice on the X and the Y. Fraction of molecules, that's like saying the number of molecules possible. Velocity, low speed to high speed. Okay, slow to fast. Distribution curve has to do with area under the curve. This is actually a calculus type of topic. We just don't do all the crazy math to go with it. But basically, say at 100 Kelvin, this is a low temperature. Versus 1,000, 10 times greater, high temperature. You're basically saying at this point in time, this yellow part of the curve, only a fraction of the molecules go at that speed. And that's it. Versus somebody that's 1,000, you have what's called a greater distribution of molecules that can go that speed. So notice some of them are very high in their curves, some of them are very long in their curves. Okay, so you have to be able to do a sketch on what it would look like, and as the curve, the peak goes down, the distribution spreads out further, and you can actually get more molecules to go at that speed. Okay, so low temperature versus high temperature. At low temperatures, okay, very slow, and your molecule distribution is very low. Versus a high temperature, very fast, and you can actually get more molecules to move at that speed. Okay, so if they're the same gas, different temperature, faster gases have more distribution of molecules. What if the temperature was the same temperature, different gases. Okay? So if there are gases with different, aka molar masses, how does molar mass affect speed? Well, think about it. You got a light gas versus a heavy gas. Which one do you think will be able to travel fastest? Okay, well, the lighter the gas, the faster the gas is. The heavier the gas, the slower it is. Same concept, okay? So all of these are different gases. This very first one, this purple, looks like xenon, okay? Xenon on the periodic table, very, very heavy mass. This light blue one looks like argon. And this yellow one is neon, and then helium, okay? Well, a heavy gas, as in xenon, only has this many molecules that can go at that speed. Whereas helium can have a greater distribution of molecules that can go at that speed, okay? So this one's a lighter gas, but has a greater distribution under the curve. I can find more molecules of helium going at that speed than I can at helium, okay? So that's what they mean by distribution. So the figure above shows the dependence of the Maxwell distribution curve, Maxwell-Boltzmann distribution. On average, heavier molecules move more slowly than lighter. Heavier molecules will have a smaller speed distribution, whereas lighter molecules have a speed distribution that's more spread out. So the heavier it is, right there, has a smaller speed distribution, whereas lighter ones have a speed distribution more spread out, like helium, okay? So you have an example, okay? What if the temperature was the same and you have three gases, okay? Draw a distribution curve by having three different gases, okay? So who's on the X and Y? You could call it fraction of molecules, number of molecules, and then velocity. So always label your axes. So number of molecules. And then we have velocity or speed. Okay? So this one is going to be different gases, which means we're going to look at molar mass. And you could just do a rough estimate. Nitrogen's 14 times 2, so he has a molar mass of around 28 grams per mole. Neon has a molar mass of around 20. Oops, my pen's tripping out. Grams per mole. And CO2, if I remember correctly, 12 plus 32, what is that? 32 plus 12, so it's around, not doing math in my head today. 12 plus 32, so what is that? 44, okay? Grams per mole. So, heavier gas, and then neon, lighter gas. Lighter gas. So, I want you to draw a curve with those three and make sure you label or color code who is which one would have a very high peak but low distribution, who will be a little bit more spread out, and who will have the greatest distribution curve, okay? So if you get a little stuck with the curves, just look at the samples above, okay? Remember, it's a sketch. Doesn't have to be perfection. So finish number 1, answer the question number 2, and I'll see you on the next one.